Hello, this is Dr. Heidelberg, and our presentation today is artificial intelligence and machine learning in mechatronics. And we will follow the reference book by W. Bolton. The topics that we will cover is closed loop control, advanced, including adaptive control, gain scheduled, self-tuning, and reference model. We'll also talk about the smart AI ML control with machine learning types, machine learning neural systems. We'll take a look at the cloud services tool for machine learning Python process, and take a look at an example of machine learning with cloud services and machine learning with Python. A typical control system has an input, it has an output, and then the process is conducted with a servo amplifier and controller driving a motor which has an amplification of force and torque driving a load. And then we have feedback loops of speed measurement and position measurements that are being summed with the desired input for position, and then calculated as the control variable desired for velocity, and continuously doing this process. So the parameters in the system are stationary. We have an adaptive control with gain scheduling, where we have the same old process as we saw before. However, the output is coming into a auxiliary measuring additional sensors that are not necessarily part of the closed loop servo. And then there is a table that checks what should be the parameters of the controller, like the PID, per range of output conditions. Now we have a self-tuning where the parameters are continuously being adjusted. We have the same old servo feedback closed loop system. But here we have a parameter estimator based on some input that is coming in from the controller, comparing it to the actual output, and then based on the difference, make an adjustment to the PID. This is another mode of advanced control, so-called with model reference. We have a model which describes analytically the relationship between input and output, and that model gets the input at the same time that the closed loop system is doing its job. But the model then is comparing its values to the output values, and then the result is causing an adjustment to the controller. The artificial intelligence machine learning is a different type of a closed loop servo system. The definition of artificial intelligence by Wikipedia is it is an intelligent demonstrated machine in contrast to a natural intelligence displayed by a human. It is in fact any device that perceives its environment and take action to maximize the chance of successful achieving its assigned task. So it's very general. A successful task could be maximizing factory throughput, minimizing process downtime, minimizing patient healing time, maximizing driving safety, minimizing cost of operation, and a general block diagram that you'll see many of them as you look at the literature. This is my perception of it, is that you are sensing the environment. You have a set of input and you have a set of output. But in addition to all of that, you teach the system, the process over here with a model, with a set of inputs that have known outputs. And that allows you to feedback continuously. You start with a guess, and then once you're done, you continuously update the parameters of your process such that the output is achieving and approaching the optimum the desired conditions. Here we see another example of a machine learning process. We see the same closed loop system that we saw earlier, but additional to the feedback loop, we feed them back as part together with additional system like accelerometers and temperature sensors. These go to some kind of a cloud service that takes the sensor's input, and then it does some algorithm computation, and then it predicts the output, and then if prediction is good, then it updates the servo amplifier parameters. If it is not good, then it is going to a machine learning algorithm. Then the model is using some external training data and improving the algorithm in this process. It should be noticed that we don't have to be data scientists. It's not the objective of this training. There are several good service giants out there that you can work with and get help. But what we like to do is make sure we understand the general AI/ML process. We like to have a persistent hands-on experience in modeling and programming processes of machine learning to understand the basic application. It's a continuous learning process. We like to be able to identify in our mechatronics devices what could become an intelligent machine or device using machine learning. And this is all state-of-the-art knowledge that would differentiate the person that knows them from a lot of other engineers out there who are doing mechatronics. It is also important to conceptualize simple, think big, but start simple models, including objective functions of your output, input sensors, and their relationship. As engineers, we should be able to know what is going to be the expected correlation, and that's going to help us a lot in debugging. If you just take it out of the blue sky, chances are that we'll spend a long time to debug it, and will drive the data scientists nuts. But if we know what to expect, we can guide the data scientists into a positive conclusion. We like to work with IT experts to improve our model, and whether it's on the edge, close to our measuring facility, or in a cloud somewhere out there, and test it, improve it, and then go ahead and run it. We want to keep on the learning process because this technology is at the singularity stage, meaning it's advancing exponentially with time. Now, who are the machine learning cloud services giants? There are IBM, there are Microsoft, there are cloud by Google, and also Amazon Web Services for cloud computing. All of these giant industry, they are leading the industry today, and they are providing the world with state-of-the-art technology, billions of dollars that they spend in educating us, making it almost easy and fun to get started with tutorials, demonstrating car racing. Start with a free startup services and have really fun in getting that learning experience. So we should take advantage of that. The first quick start with Microsoft Azure takes pretty much 11 minutes to go through. It says over here, we'll get into the system with, we have to set an Azure account. And within the Learning Studio, we'll get the data, we'll prepare the data, define the features, choose and apply an algorithm for many possibilities, and then predict the new, in this case, automobile price, okay? Given the year, the country that makes it, the horsepower, what will be the price of an automobile? This will be the exercise that we can get started with. Over here, Aju is showing us how this is drag and drop system. You see that basically what we're doing from a set of menu, we bring in the input data. We can do it from many sources, including Excel. Then we clean up the data with a lot of other tools. We erase, for example, missing numbers, rows of missing numbers and columns which are not needed. And then we split the data. Some of it we take to train the model, and the other one we take to score to see how good we did in training. So with this training portion, we also select an algorithm. What the algorithm does, it takes the data, which has input and output, known output, and try to optimize the parameters that allows us to predict the output from the input. And once it's done that, we can take that trained model and use it with the other set of scoring model and see how good we fit the two numbers, how good the two are correlated. Once we have it, with a click of a button, we can do a web application and let other people use it. The hello world of the machine learning with Python is shown over here by Jason Brownlee and developed early this year. It takes 5 to 10 minutes maximum, and he suggested that you don't need to understand, excuse me, you don't need to understand everything at this point. You don't need to understand exactly how the algorithms work. You don't need to be a Python programmer. You could actually see how it works, but cut and paste from him. And then you don't need to be a learning expert. What you need to do is have hands-on experience of a complete cycle of solving a machine learning process. Now, to get a free online Python, and we also be using C in Arduino environment, you can go to Replit, and then we download it. It's online, so you don't really have to download into your own system. And you can get examples to learn these two languages. Very popular, Python very popular in machine learning, and C very popular in microprocessors programming. You can learn it over here. It's pretty fun to do that. You can save it, and then you can use it for some examples. Here's another example of Jason Brownlee showing how we use machine learning with Python to classify Irish flower. This is a so-called hello world of machine learning. There are 4 inputs of Irish parameters and 3 outputs of Irish classification. And you see over here, this is Replit tables, pretty much following up what Jason Brownlee is showing us in his tutorial right in here. And then we follow up Brownlee's tutorial with more tables. We follow up over here the imports, the process that the machine learning goes and all the way to the final results that shows how the precision of the prediction is for each classification. We see that for Setosa iris, it's very, very good. And then for the second one, it's least good. And then the medium one is the third one. The typical learning types that we'll be doing in this course are so-called supervised learning, such as, for example, regression analysis. This is where we teach the machine like a teacher, and there are known inputs with known outputs, which are called labels. And the objective, as we saw earlier, is to predict the relationship and predict the output with a given set of input. There's an unsupervised version, which is self-learning, that finds the pattern in the data, patterns in the data without the labeling. And then there's semi-supervised, which is a hybrid of these two, and a reinforcement where each one of the iteration process they're all iterative process, but each one of the iteration process is getting a reward based on the score that they achieved. The neural networks is a very popular way of doing machine learning. There is a description over here, shows a set of inputs, a set of outputs, and hidden layers. When you have one hidden layer, it's a simple neural network, and when you have several hidden layers, it's called a deep learning neural network. And these inputs could be machine parameters, various machine parameters. And there could be output various levels of performance. It could be various inputs for health therapy parameters and variables. And the output could be the scoring of the patient and the doctor as how well it was done. And the objective is to find the best set of parameters that will result our objective functions to be maximized. And of course, our skill set is to look at our system, whether mechanical, electrical, mechatronics, and be able to identify which sensors shall we use here and which is our objective functions that really would provide the best benefit to our customer. Now, the example of supervised machine learning with regression is given by Raman Shah. We see over here a training process. The process says that a real y equals to x1 plus 2x2 plus 3x3. Now, x1, x2, and 3 could be a velocity acceleration, path radius in some kind of a scribing, 3D scribing operation. And then y, the output, could be a dynamic accuracy that we like to minimize. So over here, you see that all of this trained model is giving us the exact result. When we run the regression analysis, we assume that the output is a coefficient in front of x1, plus a coefficient b in front of x2, plus a coefficient c in front of x3, such that when we have x1, x2, x3, we would like to predict y with y sub bar. And then we want to find A, B, and C with the machine learning process, which will minimize the difference between the predicting value and the actual value. And here we see, again, with Replit, the program, pretty much step by step as shown by Raman. You can cut and paste and observe the process in minutes. And then you see over here that the test data was 10, 20, and 30. We calculate in this formula, the actual is 140. But then the outcome was also 140. And the reason is that the teaching sample was exact. Typically, there are random variables, and then we will not have the exact value, we'll be close to it. And then the optimum A1, A and B and C are exactly as the real process. Has X1 has 1, X2 has 2, X3 has a coefficient of 3, and this is what the machine learning program found out. The last example is by James Loy, and what we see here is an example of using a neural network for machine learning to classify a picture. Now, in this classification, there could be thousands of these input variables. Each one could be a microscopic pixel with the color of that pixel and the level of shade. And the output that we like to predict is whether it's a cat or a dog. Now, in our environment, in a more engineering type of environment, if we take, for example, a therapy device, mechatronic therapy device, we call it IsoWipe, and we input force, vibration, and time instruction to the patient. We would like to get an output for the patient about the pain level, a discomfort perhaps, how hard it was, how easy it was, and was progress in a healing process. And what we like to do is continuously update the relationship, which is very difficult to predict otherwise, between the output and the input, such that the output, the desired output, fastest progress and easiest way of doing it will be maximized, and the pain and discomfort and the hardness will be minimized. Here we see the formulation and neural networks very nicely done by James Loy, and it shows the process. I'll spend a few minutes in doing it, but I recommend that you follow up with this on his tutorial. Many people have given claps for that. Now we have here the input vector of input variables, and we have the output vector estimates of outputs. Then we have the vector of hidden layer, where we take here 1 for the simplicity. Now, the way we do it is we assign a value A to each one of these neurons. By the way, it simulates the way a human-operated brain is functioning. And we take for each one of the inputs, we contribute to the value of A by a weighting function, W1. Now, this is W11, W12, W13, and so on and so forth, plus a bias. And we take that and we bias up and down. So we have vectors of bias and weights. Similarly, we have bias and weights from the relationship between the hidden layer and the output. And we have here some definition that we define Z as the weight times the input plus the bias. And then we define another function, A, which is the value over here, the hidden layer, which is some type of sigmoid function. The sigmoid function looks like an S, and what it has minimum of 0 and maximum of 1. So the number over here of A could be either somewhere between 0 and 1, depending how strong is the weighting and the bias. And then we have we take all the values here and we hit the output with another W2 and B2 of the values in between the layer and the output. This gives us the expected output. Now, our objective function or our loss function is the sum of the differences of all the inputs and all the actual outputs and the predicted outputs. And then we square it and we sum them up. Now, in order to improve the process, we want to change now the weighting functions and the biases such that it'll get us closer to the real Y. And the way we do it is we use differentiation. We take the function of the objective function with respect to all of these variables. We differentiate it by parts. And then we take that derivative and we multiply times the old weighting function and bias in order to give us a closer result to a better output. And then we run it with the Python configuration. It may get a little bit complicated, but you see over here there are dot products of the vectors. So the Python is doing some matrix algebra for us. And at the end, what we observe is that the convergence is taken step by step throughout the iteration, the learning iteration, until we converge to the point where the output and the predicted output are very, very close to each other, and that's where we can use it in process. This completes our presentation, and we'll see more of that in upcoming exercise. Thank you.